Welcome to Hartman Math. Today we're going to be discussing combinations of functions and focusing on composite functions. But before we get to that, a little bit of warm-up, some review problems, getting into that, some of the work we've been doing with functions. So go ahead and pause the video here, work through 1, 2, 3, and 4. Number 1, first it's asking for the domain. The domain of this function is bracket 0, comma 6 parentheses. Due to this, for the numerator part, the domain of that part of the function being bracket 0 to infinity. And then looking at this one, just as itself, the square root of 6 minus x, if you were to say that 6 minus x has to be greater than or equal to 0, and we solve that, we're going to see x has to be less than or equal to 6. So basically, parentheses negative infinity, comma 6 bracket. But also remember, you can't divide by 0. So that throws 6 out. So that's why 6 is now a parenthesis instead of a bracket. Number 2, we've got a composite function. We've got a parabola part. So part of a parabola, which would normally have come down to a vertex right here, and that part, but we're saying x has to be less than or equal to 1. And then over here we've got a line part with a y-intercept of 1 and a slope of 2, and x having to be greater than negative 1, and therefore an open circle there at that endpoint there. Number 3, sketch f of x. We were just recently working on this with transformations. We've got our square root base graph or parent function. We've got the reflection in the x-axis, and then the 2 is just like it would be adding 2 over here, so we have a shift of left 3 and up 2. Left 3 and up 2 with the reflection, so showing key points, there's our graph there. And then lastly, and I know sometimes it can be hard to see on some of the bottom stuff here, so part A, f of x equals x cubed plus x squared. We work that out, turns out to be neither. H of x equals negative 2x to the 4th plus 3x squared. That is even. And k of x equals x to the 5th minus 8x to the 3rd. And that happens to be odd. So if you have questions about any of those, bring those questions to class. So combinations of functions, if we look at arithmetic combinations, we're talking about adding, subtracting, multiplying, and dividing of functions. So we've got the sum function, where we just add them together. The difference function, where we just subtract the two. And the product, we multiply the two functions together. And the quotient function is where we divide them. Most of the functions that we tend to work with are polynomial functions. And one of the things that you've been exposed to this before, we're really going to kind of review that, but also really be thoughtful about the domains of the sum function, difference, product, and quotient. Now, if we're working with polynomial functions, here and here, f of x and g of x, then the domain has to be all real numbers for each of the functions, and the sum function as well, and the difference, and the product. But see, here's a little bit of condition here for the quotient, because when we're dividing, we do know that we're not allowed to divide by 0. So any value of x that causes us to divide by 0 has to be excluded from the domain. So we're saying x cannot equal positive or negative 1, because then we would be dividing by 0. So domains, that's what we were just talking about. Okay. So in summary, just kind of look at the notation. You might be more familiar with it looking like this, but it may be asked like this. F plus g of x just means do f of x plus g of x. It's just notation. And for quotient, we have to be very mindful of the domain, making sure that no value of x causes us to divide by 0. So now we're going to start looking at some functions that maybe are a little bit less obvious in terms of domain. So maybe not polynomial functions. F of x is not and g of x is not. So f of x is the square root of x. So if we think back to our library of parent functions starts at 0, goes to the right, and that's why the domain would be bracket 0, comma, infinity, parentheses. And g of x, remember that was that reciprocal function in the parent functions. And if we think about this, well, that just means x is really not allowed to be 0. We can divide by 5, we can divide by -2, we can divide by 0.7, divide by 2/3, just can't divide by 0. So just x is not allowed to be 0. And there are other ways of writing that. But we're doing this informal because our goal here is to find the product function and the domain of the product function, not just necessarily each. But we do want to think of each one because we're going to talk about what overlaps in that case. So the product, we would just multiply these two together, and we would get the square root of x over x, and the domain would be the overlap between these. So from 0 to infinity, but no, we can't include 0. So how do we exclude 0 from this domain? We don't want to go to 1 because we don't want to exclude a half, a third, 0.7. We're just going to turn that into a parenthesis to say 0 is not in our domain because of this. Example number 4, quotient function. We already talked about g of x, I'm sorry, f of x. Here's a new g of x. G of x equals the square root of 4 minus x squared. So we're going to think domain here. We already know that one. G of x is going to be a little trickier to find the domain. It's not a function entirely that we're really kind of used to. Now you might think, well, I can just do 4 minus x squared is greater than or equal to 0, and that is true. That's a good way of looking at it. But this is a pretty complicated one to solve as an inequality. We could factor it as a difference of squares. So 2 minus x and 2 plus x is greater than or equal to 0. And then once we do that, one of the strategies that we're going to kind of work through at some point in this course is to come up with the boundary points and say, all right, so we've got on the number line, we've got 2 and -2 are the critical numbers, or the zeros. If this was equal to 0, those would be the zeros of, or the solutions to the equation. And then we can kind of test the regions or something like that. So back into our original, pick something like -5 out here, try -5. Does 4 minus -5 squared, is that greater than or equal to 0? That's false. How about picking something in the middle, in the regions there, like 0? And that's true. And then something like 7. Plug in a 7, and that's false. So that's one way, or you could just think about plugging in numbers. Is it allowed for me to plug in 4? No, I'd be taking the square root of a negative. How about 3 and 2? And you just kind of want to play with it. But this kind of tells us where our domain is going to be, and it's everything between -2 and 2. So now the quotient function, f of x over g of x, is that. What's the domain? We've got not only to combine these two, so basically doing the overlap between these on the number line. So if we were to look at that, so 0, all of those, and -2 to 2, all of those. Where's the overlap? It's right in there. But one more condition is that we're not allowed to divide by 0. So any number here that causes us to divide by 0, we got to throw that out as well. So from 0 to 2, but we can't include 2 because when we plugged in a 2, we would get 0 in the denominator of our function. So that's why we're excluding the 2, and we show that with parentheses. Composition of functions. We've got f of x, we've got g of x, and here's our composition. We want to do f of g of x. So we want to essentially plug g of x into f. For example, if we were doing f of 5, we'd substitute in a 5. But we're doing f of g of x, so we're going to, into the f of x, we're going to replace the x with g of x. So here's our first substitution. Replace g of x with x plus 1. Here's our second substitution. We're replacing the x in the f function with the x plus 1. So x plus 1, use parentheses when you substitute, gets squared. Also notation, f open circle g is read as f composed with g, or you could just say f of g. So it's not a closed circle. It does not mean multiplication. It means composition. It means exactly that. The domain is pretty tricky. It just means that the domain for f of x has to match with the range for g of x. So we have to make sure as we plug it in, whatever comes out to g of x, that's what's allowed to be plugged into f of x. So we'll really kind of look at the nuts and bolts of that coming up. So just a definition where, as I said, this matches with this. They mean the same thing. And then when we're talking about the domain, once you get your textbook, it's figure 1.55. It's really complicated to look at and read through. It's easier to see in an example what we're talking about. Example number 5, find f open circle g of x. The second function listed is your inner function. So we're going to say f parentheses g of x. That could be a place for us to start. So there's our inner function. Now if we look at the domain, what actually matters is what is the domain of the inner function. The outer function really doesn't matter for its domain. We want to first analyze the domain of the inner function. And it's just an mx plus b situation, or you could think of it as a polynomial. So we would know that that is all real numbers, or negative infinity to positive infinity. This is informal, so I don't have to list it in a particular language. So now I'm going to say f composed with g of x. I'm going to write it as f of g of x. And my first step is to replace the g of x with the 3x minus 2. And then so 3x minus 2 gets replaced. It replaces the x there and the x there. So 3x minus 2 gets squared plus 5. Replace the x with 3x minus 2. So maybe on some side work, we're going to do 3x minus 2 squared. No, you cannot just distribute the exponent on the side. Do 3x minus 2 times 3x minus 2. Do all the multiplication that would be involved in multiplying the binomials. And then just a simple distributive property over here. So this part over here gets us 9x squared minus 12x plus 4. And then 15x and minus 10. Combine your like terms, and we've got our final answer. Yes, that is factorable. We were not instructed to do so, so we're just going to leave it like this. Second part, what is the domain? Well, we would be concerned with what's the domain of this. And that's just basically a quadratic function, a polynomial function also. So if we overlap that, all real numbers, with all real numbers, we're going to get, from negative infinity to positive infinity, all real numbers. Example 5, part B. Back to our f of x being the square root of x, and g of x, pretty simple, x minus 1. Notice the directions here, g of f of x, the second one listed is f, and that becomes our inner function. So we are concerned about the domain of that inner function. We would say that x has to be greater than or equal to 0, or we could say bracket 0 comma infinity. So now let's write it out, g of f of x. The f of x is root x. That's going to get plugged into the g function. So as we go to the g, the x gets replaced by root x. And there's only one of them, so just the square root of x minus 1, no simplifying needs to be done. So now the domain to that. So we're going to have to look at this, and what's the domain here? Because again, we have the situation where we're taking the square root of x. So it's bracket 0 comma infinity, and that overlaps with this, and they are the same, so they have the complete overlap of bracket 0 comma infinity. So we're always going to look at the domain of our final answer overlapped with the domain of the inner function. And that may not always completely coincide, and I think we're going to see an example of that shortly. Example 5, part C, f of g of x and its domain, new f of x, new g of x. All right, so second function listed is g of x. That's the one that's our inner function. That's the one that we want to know the domain of. Probably should have it over here. But what's the domain of this? We've seen one similar to this with this square root 9 minus x squared. So again, you can kind of think about that, pause it here, kind of see if we can work that out. What values of x am I allowed to put in there? And it turns out that it's bracket -3 to +3. Anything between -3 and 3 we can plug in. Anything that's outside of that, like a 4, we plug it in, we get a negative number underneath the square root sign, not a real number. So now let's go ahead and do the f of g of x. We're going to replace, into the f function, replace the x with this. So our term there, squared minus 9. And the square ring and the square root cancel each other out. So we get 9 minus x minus 9. And from that, we would get an answer of -x squared. Now the domain for that. Well, the domain for this itself is all real numbers. -infinity to +infinity. It's just an upside down parabola. But we do have to overlap that with this domain over here and say, all right, so the overlap between all real numbers and from -3 to 3 ultimately is from -3 to 3. So this is for there, but the answer to the domain for f, the composition, is right here. It's the overlap between this and this. Let's see if we can make sense of it, because this is essentially our function here. If I tried to plug in 5, immediately I go 9 minus 5 squared, that's -16, the square root of -16. Now we're talking into imaginaries, even before the square. So there is the issue. So make sure we take the domain for your final and overlap it with the domain of the inner function. Okay, checkpoint. We're going to find the composite function h of g of x and the domain for that composite function. Go ahead and pause the video here, see if you can work it through, get both parts. Okay, g is the inner function. Its domain is bracket 0, infinity. As we plug it in 1 over and replace the x with the inner function, we get the function 1 over x, so that's the composite function. We know that x is not allowed to be 0 there, and if we overlap these two, the overall answer domain with the inner function domain, we get, well, we have to exclude 0, so we get parentheses 0, infinity. Example 7, the next thing we're going to look at is decomposing a composite function, essentially undoing that work. If we had the composite function, what would be the parts, the f of x and the g of x, to make that happen? The symbol here does indicate this is kind of a calculus skill, something that would be beneficial in a calculus class. So we're going to start with the inner function, so kind of look inside, look around the x. And the thing about these, there's often more than one answer. But if I was going to really focus around the x, I might say that my inner function would just be the 9 minus x part. So remember, the inner function is going to be the one that's listed second. So that would be a good inner function to use. And then the outer function. Well, what is happening to your inner function? What is happening to the 9 minus x? It's being square rooted. So that's the outer function. It's just being square rooted. In general, the input is being square rooted, and the input is just generically x. So f of x would be the square root of x. And if you wanted to then work it out and kind of do it like a previous example, you would see that if I compose these in this fashion, that is what we would get. And last thing we're going to look at is one of the things that they might be asking you to do is to do composite functions just based off of a graph. And so in order to do that, we need to be able to evaluate based on a graph things like, hey, if this is f of x, what is f of 3? That's all according to the graph. So if we look at it, the 3 has taken the place of the x. So in the graph, 3 is the x-coordinate. Now let's go to the graph. Where on the graph is there an x-coordinate of 3? Not here, because I'm not on the graph. I have to be on the graph of the function, somewhere here. Where on here is the x-coordinate 3? Right there. Now, f of x is the y. So really, I'm asking, hey, what's the matching y-coordinate here? And it would be 4. And what would be f of 4? You got to be on the graph, so where is, right there, that's where the x-coordinate is 4. Go across, and I've seen I've got an answer or a y-coordinate of 2. So you're going to be asked to do something like that because you might be asked to do on a graph f plus g of 3 based off of 2 graphs. So use that technique to come up with the function values. That's it for today. We'll see you next time.